Okay, so 8-8, strengths of covalent bonds. This is good stuff. It's actually got quite a bit of application in a lot of different areas, but it's also going to throw you a little bit because there's a calculation that's almost opposite of the products minus reactants that we learned in the thermodynamics unit, or the thermochemistry unit, I guess. Technically, we haven't done thermodynamics yet because we haven't talked about the entropy. But anyway, all that to say, we're covering 8-8. And I guess if you're following along in your book, that starts on page 325. You can, if you want to. I'm going to do probably one example out of the book, I think. 325, yeah, page 325. Okay, so here's where I sort of gave away the punchline to this section. So even though this is technically something we didn't talk about last year, it still might feel a little bit like review because we have been talking about it. All right, so this is really the only thing in Chapter 8, really in Chapter 6, 7, or 8, that's from the book that's kind of brand new to you, okay? You know, there's been some other stuff that I've supplemented, like the TES stuff, which is not in the book that we had to talk about. But it's basically just talking about when you're breaking or forming a bond, okay? And so bond enthalpy is basically that's how much energy it takes to break a bond, okay? So I wish I had this chart available so I could show it. Actually, I might in one of my old set of notes. Let me see if I can pull up the chart, because we can talk about something useful with the chart, if I can find it. That would have been from, I think, 2 years ago. And where are you? This one, I think. No, that's not the notes. Sorry. Yeah, I need the PowerPoint. This one, I think. Or we could do Cheerios. Cheerios. Let's see if I've got the chart in here somewhere. I feel like I will. Yeah, there we go. Is that it? There, okay. Although this may be slightly different. Well, no, I guess you can see that okay, can't you? Can you? No? Okay, sorry. So, all right. So, single bonds versus multiple bonds. All this is showing here is the bond enthalpy, okay? And the bond enthalpy is usually measured, it's not labeled here, but it's usually measured in kilojoules per mole, okay? And basically that's just how much energy does it take to pull these things apart, to break this bond, okay? Now the reason a bond forms in the first place, a covalent bond, really any bond, the reason that it forms is because of an attraction, electrostatic attraction, right? So in a covalent bond, what's attracted to what? Yeah, positive and negative, right? So, but if you think about this, when a carbon and a hydrogen move together, there's protons in the carbon and the hydrogen, right? So the protons probably repel a little bit, right? But it's the electrons in the carbon that are attracted to the protons in the hydrogen, and the electron in the hydrogen that's attracted to the protons in the carbon. That's what causes this to stay together, okay? So it's that attraction. Now there is a little bit of repulsion there that keeps them from getting too close to one another, but there's that perfect distance between the two of them where the electrons are attracted to the nucleus, but the nuclei are not so close that they're repelling each other, okay? And so that's basically what's going on here. So in order to break these apart, it takes energy, right? Because they're attracted to one another. And so if you look at the energies here, you might be able to start noticing couple of things. So let's look at some of the things. Well, first of all, if you look at the difference between the bond enthalpies of single bonds versus multiple bonds, what do you notice right off the bat there? Which ones are higher? Yeah, the multiple bonds are quite a bit higher. This is on page 326 in your book. I'm not sure if I said that or not, but the multiple bonds are quite a bit higher, okay? Which, does that kind of make sense? I mean, if you've got a double or triple bond, it makes sense that it would take more energy to have to, to break those apart than it would to break apart a single bond. But then we can look at some other things up here. For example, you can just kind of compare some of these things to one another. I've got a carbon-fluorine bond right here that's 485 kilojoules per mole. I've got a hydrogen-fluorine bond right here that's 567 kilojoules per mole. Is there anything else with fluorine? Nitrogen-fluorine, 272. Sulfur-fluorine, 327. Bromine-fluorine, 237. Okay, so I'm just looking for things that are... Sorry, looking for things that are... Are there a couple more? Oh, okay, sorry. Chlorine, fluorine, and which one? Oh, fluorine. Ha, yep. There we go. Okay, so there's kind of a trend here, all right? What's the lowest energy, the easiest one to break? Fluorine. Interesting. And then the hardest one to break looks like it's the hydrogen fluorine, right? Any ideas why that might be the case? Kind of just looking at the periodic table. Yeah. They're perfect for each other.
Yeah, they fit perfectly.
Okay, but this is not an ionic bond, all right? So this is not like a full transfer where the hydrogen is giving away its electron to the fluorine. This is actually considered a covalent bond. Okay? So why is it takes so much energy to break that one apart? Okay, so for one thing, hydrogen's small, right? The smaller they are, the closer those electrons can get to the protons without that repulsion happening, right? And the closer the electron can get to the other protons, the harder it is to pull those apart because they're more attracted to each other, right? So that's one thing, okay? So the smaller they are, typically the stronger the bond they will form. Now that's true not just for covalent bonds, that's true for ionic bonds as well, okay? So you've got a smaller ion, like a lithium, combining with a fluorine. That's going to be hard to break apart, right? Because those ions are smaller, they can get a little bit closer to one another, okay? And so then you've got a stronger force of attraction there, okay? As opposed to a potassium and a bromine. Does that make sense? Okay. Yes, ma'am.
What is
Si and Cl. Okay, so the Si-Cl bond right here, why is that one so strong? Well, okay. So that actually leads us into kind of the other reason here. Okay, it's not just size. There's another reason. Now, what do we know about fluorine-fluorine? They're the same. So is there any polarity to that bond whatsoever? No, I mean, it's just two fluorines, right? They're sharing equally, okay? So that bond is not polar at all. So that one's a little bit, if you have the equal sharing, it's a little bit easier to break. Now, what about the hydrogen-fluorine bond? Okay, you see how, I mean, you've got hydrogen all the way over here on the left. It's not as electronegative. You've got fluorine all the way on the right. So you've got a lot of polarity there. So the more polar the bond, typically, the harder it's going to be to break, okay? So that's kind of your two general trends that I wanted you to look at as far as the bond enthalpies. What else do I want to say about that? think that's pretty much it. Let me see if I have this picture. Actually, now that I've got this thing open, maybe I can just use these pictures here. No, too far, or not far enough. There we go. Okay, this picture. So this is on page 327 in your book. So this is showing you what I was trying to tell you the other day about all of your biology classes, right? About the breaking and forming of the bonds. Okay, so really, it's not because glucose gets broken down that your body gets energy. Okay, it's the bond forming part of that process that releases the energy that your body needs. Okay, and so you look at something like CH4 reacting with Cl2. Okay, so methane and chlorine gas, when they react with one another, the first thing that has to happen is you have to break some of the carbon-hydrogen bonds in the CH4. And then you have to break the chlorine-chlorine bond. Okay, now the reason that's an up arrow is because it requires energy for that to happen, right? In order to pull that hydrogen off the CH4, in order to pull these two chlorines apart, that's going to take energy, right? Now, once you have provided that energy, now you've got a free hydrogen and a free chlorine. When they come together, that's going to release energy, okay? So that's the opposite process, bond formation. And then when the chlorine comes together with the CH3 that's left here, again, it's going to release energy. Now, because it releases more energy ultimately than the amount of energy it took to form it in the first place, what kind of reaction is that going to be? Exoendothermic. So we put in this much energy. We put in the energy delta H1. The amount of energy given off is the delta H2. Which one's larger? The amount of energy given off is larger, right? So overall, this is an exothermic reaction. Okay, the amount of energy we put in is less than the amount of energy that it gives off. Okay, so ultimately, some heat is going to be released in this reaction. Does that make sense? Okay. Now, we have to put some energy into it to get it started. By the way, you remember this this diagram from the last test?
Yeah.
This right here is because we have to put some energy into breaking the bonds in the first place. That's why you've got that little, this is called the activation energy, okay? It's the little hump right here you have to get over before it starts to release some energy when the two things come together, okay? Does that kind of make sense? The axes on this, just reaction progress going this way. So essentially it's just as the reaction proceeds over time, and then the y-axis is the potential energy, right? Okay? So, so that's just the basic idea of the bond breaking, bond forming thing. You just really need to remember that when a bond breaks, that requires energy because you're pulling two things apart, okay? When new bonds form, they release energy, okay? All right, what else do I want to talk about here? I may even have the same sample exercise in here. Let's see how much they've changed this book in the last 10 years. Oh yeah, this is fun. Oh, it's the same problem. It's funny. Well, I guess you stick with what works, right? Yeah, it's the exact same. Okay, so sample exercise 812 in the book, page 328. This is another way to figure out the delta H of a reaction. So remember, in the last, sorry, in the last chapter, there were a couple of ways to figure it out, right? We could either do Hess's law, if we knew a couple of other equations that were related to this one, then we could make them add up and figure out what the delta H for this reaction is. The other thing we could do is use the heats of formation, right? If we know the heats of formation for all of these things, then we could do products minus reactants, and that would give us the delta H. You guys remember doing that? So I'd find the delta H of formation of the H2O the delta H formation of the CO2. I don't need to find the delta H formation of O2. Why not? Because it's 0, right? And then I find the delta H formation of the C2H4, okay? I take the products minus the reactant, the 1, and that would give me the overall delta H for this equation, okay? Now, there's another way that we can figure this out, okay? And I almost don't like giving you a formula for this one because it's almost the exact opposite of the products minus reactants thing for the delta H of formation. But basically, we need to figure out the energy it takes to break these bonds versus the opposite of the energy it takes to break these bonds. Why the opposite? So let's say I figure out how much energy it takes to break these bonds right here, okay? Why would I want to use the opposite of that energy when I'm doing my calculation? Yeah, because these bonds don't break in this equation, they actually form, right? So theoretically, the amount of energy it takes to break a bond, that's exactly how much energy should be released when the bond forms, okay? So let's see if we can figure this out. And you're going to have to use that chart on page 326. Okay? Now, the way that they drew this out was kind of nice for you so that you can see exactly what bonds are breaking and what bonds are forming here. Okay? Let's see. So we've got... Let's just say theoretically. Now, it may not happen this way, but let's say theoretically when this chemical reaction occurs, all the bonds on the left side break, and all these new bonds form on the right side. Okay? So let's figure out how much energy it would take to break all the bonds on the left side of the equation. So we've got 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds that have to break, right? Okay? How much energy does it take, according to that chart, to break a carbon-hydrogen bond? 413 kilojoules per mole, okay? So 413 kilojoules per mole, and basically we're breaking 6 of those, so we have to multiply it by 6, okay? So 413 times, we'll just say 6 moles of bonds being broken here, okay? Because we're dealing in moles when we're looking at the overall equation, okay? And then I'm going to add that to the amount of energy it takes to break the O2 bonds, right? Because we'll have to split the oxygens up from one another as well in order to make this reaction occur. So what about an oxygen-oxygen bond? Oh, yep. Well, yep. Forgot about that. Carbon-carbon. We need to break the carbons apart, right? So how much energy does it take to break a carbon-carbon bond? 348, okay? 348, and there's only one of those, okay? So you can say kilojoules per mole times 1 mole if you want to. Don't necessarily have to do that, okay? Then 7 halves O2. Okay, so it takes 146 kilojoules per mole to break an oxygen-oxygen bond. Does that make sense? You guys see that? So 146 kilojoules per mole, and this is a little weird. How many moles of oxygen do we have in this equation? 7 halves. Okay. All right. So that's the reactant side, right? That's how much energy would need to be absorbed by this thing to break all the bonds on the reactant side. Okay? This is where I really wish that I had my big calculator, and I can't find it anywhere. Yeah, can I borrow a calculator? Makes me really sad. I liked that calculator a lot. I don't know what happened to it. I probably put it somewhere and just haven't found it yet. Or Jeff did something. Oops, I said a name. or, random student.
Well, you didn't say a last name.
I didn't say a last name. That would have been bad.
So don't say it.
I won't say it. I was thinking about giving a hint, but I'm not going to. Okay, so I'm getting 3,337 kilojoules, okay? So for us to break all the bonds in the reactants, it would take 3,337 kilojoules, okay? Now what we can figure out is, okay, how much energy gets released in the products here, okay? And so we kind of have to go about this a little bit strange because we don't have any bond formation numbers. We just have bond enthalpies, which is the energy it takes to break the bonds. So let's say that we are going to break these carbon-oxygen bonds, okay? There's 2 of them that need to break in CO2, and then there's 2 moles of that, right? So how many total carbon-oxygen bonds are we going to break here? 4, right? Now, these are double bonds, not single bonds. So this is going to be, we'd have to look at the bottom of this chart here, 799 kilojoules per mole times 4 moles, right? Everybody follow on that? Okay. Plus, on the water, we have to break 2 oxygen-hydrogen bonds. But again, since this is 3 moles, it's going to end up being 6 oxygen-hydrogen bonds. So oxygen-hydrogen is 463. Multiply that by 6. Okay? So kilojoules needed, we'll say here. Okay? And then when I work all this out, I'm ending up with 5,974 kilojoules released. Right? Because we kind of have to think backwards here. If this is the amount, if 5,974 kilojoules is the amount of energy it would take to break all these bonds, then we're going to assume that that's the amount of energy that gets released when those bonds form. Okay? So if we need 3,337 kilojoules and 5,974 kilojoules get released, then is this exothermic or endothermic? This is exothermic, right? We have a lot more energy being released at the end of this reaction, which kind of explains why this reaction occurs, right? Okay? Which we haven't talked about that a lot yet, but one of the reasons this will occur is because you end up having a lot lower potential energy on this side of the reaction than you did initially, okay? And these chemicals like to move to a lower potential energy state. Just like tape that's up here on my desk likes to move to a lower potential energy state by falling down, okay? So it's very similar to gravity. Anyway, to figure out the overall delta H of this reaction, now all we have to do is take the amount the amount of energy needed to break the bonds, the 3,337, minus the amount that gets released, 5,974, and that's going to give us our delta H. Which is negative 2637 kilojoules. Which, that's a lot of energy, right? Kind of makes sense also because this is a combustion reaction, right? Combustion reactions release a lot of energy. There's fire. There's heat, okay? So that's another way to calculate the delta H of a reaction using those bond enthalpies, okay? So just wanted to run you through that. I think that's basically what we need to talk about. The one other thing that's in here is bond enthalpy versus bond length, okay? And that kind of comes back to, I'm going to do this very quickly because we're basically out of time here. But that comes back to this idea: the multiple bonds are the ones that are they take more energy to break. Now, part of that reason is when you have a multiple bond, that actually moves the atoms a little bit closer to one another. So the closer they are to one another, the shorter that bond length, the harder it is to break. Okay. So that's the basic other idea that's in here, but I think kind of makes sense already. Yeah. Oh, did they have a different answer? Did I mess up? I probably. Oh wait. Negative 1416.
They got a bigger number for the energy needed. Yeah.
Where did I mess that up then? It's possible. I may have just messed up a number. 495. Yeah. Sorry. I'm not sure where I messed that up. Let me see. If I messed it up in my setup or in my calculation. I can find it. Is it? So you got 6 times 413. And then 495 times 7 half. 495? What? That's where it is. It's the O2 bond there. Ah, because O2 is, yeah, it's a multiple bond. Sorry. That's my fault. Okay. So that should be 495. Instead of, so right here, instead of 146, that should be 495. Okay. Yeah, you're still going to get a lot of energy out, but not quite as much as we calculated. So you should end up with 4558 for this number instead. 4558 kilojoules. And 5974 is right. So then you end up with negative 1416. Sorry about that. Yep. My fault. No, I'm glad you corrected me before I turned the video off. Okay.
Wait, how do you know it was deadline?
Got it? Okay. All right. So that's that. And we will probably cover the bond energy stuff a little bit more in class on Wednesday, I think. Okay. Sorry, that was a long one.